Okay. So welcome to Fluid Dynamics. I think I know almost everyone except for Andrew. Is that right?
Yeah.
Okay. So I guess I'll tell you about me. So I did my undergrad at Santa Cruz in physics, or what did I do? Astrophysics, something like that. It's like 3 decades ago. And then I went and I got my PhD in Colorado, and I went to Maryland for postdoc, where I work with basically I'm a planetary scientist. So you can see my research up in the corner left there. I study the Martian atmosphere, and we use 2 spacecraft to do that, amongst other things. But the 2 that I'm a team member on is the MAVEN spacecraft and the Trace Gas Orbiter. So I like fluids. You'll find out today that gases are fluids. So they said, you don't have to teach 2 classes. And they said, you can just teach 2300. And I said, but I love them so much. And they said, okay, fine, you can teach another class. They wanted me to teach stat mech. And I said, that sounds boring. So I want to teach you about fluids instead. That sound good? Okay, everyone excited?
Yeah.
Anyone worried? Yeah. Okay. You say no? Oh, okay, good. You should be worried. No, just kidding. What is this?
Water.
Good. What are the processes you see here?
Falling.
Okay, something's falling.
I see ripples.
You see ripples. Good. What's that? Waves. Yeah, waves would be in the ripples here. Anything else? Yeah.
I think it's called an impulse, where it like comes back.
Okay. Yeah. It looks like there's some reflection here.
Yeah.
Both actual reflection and reflection in the water. Surface tension. Good. That's one of the ones I wanted.
Displacement.
What's displacement?
Like the water being displaced.
All right. So there's some missing mass here. Right. There's flat here, non-flat here. Okay. A lot of my class, you've taken, say, 2300 with me, it's all up here. Okay. In my computational physics class, we did a lot of shit like on the computer. Here, we don't have a wet lab. Now, I wanted a wet lab. It's very expensive. So if you want to do all of these demonstrations, it's very hard to do. So we're going to use mixed media. Okay. I'm going to show some stuff. I'm going to write equations on the board, and then I'll show stuff, and I'll write equations on the board. You're welcome to take your notes here. We're going to talk about that in a few seconds. Any questions before we get started? Okay. Hello. Why does everything break? Okay. So what you'll need to succeed in this class is the textbook. Earlier versions are fine, but you are responsible for any differences in the page numbers, equations, etc. If you have a question about that, that's fine. We'll get to that in a second. This one's important. Okay, motivation to learn. I'm going to try and make fluids fun. Some of it will not be fun. Some of it will be annoying, particularly the math. That's when you got to dig deep into those wells. Okay. You'll need discipline and accountability, and I'll tell you why in a few minutes. And you'll need to communicate. Okay, you'll need to communicate with one another. You need to communicate with me when you don't understand something. It means raising your hand. You see something you don't understand, you're like, well, I don't want to like bother the whole group. That's the wrong instinct. Okay. Don't get something, just ask. Okay. So we are going to do something called ungrading. What is the purposes of grades? To tell you what?
Oh, sorry, never mind.
Yeah, go ahead. Don't read. I'm asking you your opinion.
You're doing it.
Good, yeah. They're about a form of assessment, right? Okay. Is it always fun? No. Is there any way that grading could be a hindrance to learning?
Sometimes just getting a number like out of the scale isn't necessarily the best. It's like what's the difference between a 6 and a 7 really? Like we all know the difference between a 0 and a 10 from a scale of 1 to 10. What's like the difference between 6 and 7?
Sure, yeah. How granular it is, right? Have you ever looked at an assignment and then seen what you got on it and not opened it?
Mm-hmm.
It's been like, oh, I'm happy with a B, or I already knew I was going to get a C, right? Okay, so we're going to remove that. Any other ways that grading is detrimental?
Focus more on the grade than actually learning the content.
Actually learning the content, right? So this class is going to be very wide. Okay, but it's not going to be very deep. The reason it's not going to be very deep is because fluids are a very large subject. So I will be asking you personally to cover a large swath of material. This whole book, essentially. That'll be in your brain. Now, how well it's in your brain is up to you. Okay? So you can get exactly the grade you want. You want a D? That's fine. You want an A? It's fine. You're gonna make an argument for it. So, what did I say here? I'm gonna have to read a lot of my own shit. I'm dumb. Okay, so what I mean by accountability is you're gonna hold yourself accountable. That means that when you come into class, you will have already done the reading. I know this seems like an incredibly opaque concept, but these books, you'll notice that I have a lot of them. Why is that? Why do I have so many books in my office?
Because you read them.
Because it's helpful. Because books help. Do I know what every page says? No, and neither should you. But you should know where to look. Okay? The process of science is determining where to find the information and what's credible and how to use it. That's what we'll be doing in this class. So these are what I call bonus books. You can buy, this one's like history. You like it. Oh, this is fun. But I hate science outside of class. Okay, well then you're in the wrong field. And then this one here is computational fluids. Well, I hate extra work. Again, wrong field. These here, this is what I learned on. You can tell it's ratty as fuck. Doesn't even have the stuff at the beginning. And so at the beginning of this, there's a really beautiful lexicon. And you'll see that definitely if you have the 6th edition. Open up the 6th edition and go to page XVII. It has every symbol and what it means. You'll need that. Okay, so you can use this one. I would recommend this one if you ever decide that you want to stay in like planetary science. If you want to go into engineering, this is a book to have. If you don't want to have this book, these are fine. Questions? Okay. So that's the accountability part. If you make it to the end of the semester, having learned the material, you'll get the grade you deserve. Okay? And you'll make that argument. And I'll show you how. So we're going to start with progress reports. If you don't have a computer open, please open a computer. Okay? We have these Google documents. We all love them, right? Super helpful. You're going to have one for this class. And it's going to be progress report and your name. You're going to replace this italicized your name with
Actual name.
no, with
My name.
Last name.
with
Oh.
Kobe. There you go. I'm actually not you. No. What's your name?
Oh.
There you go. Okay. So don't be funny in here and put the last name, actual name, your name. Put your name. Okay. That's for clarification. And then you need to share it with me. This needs to happen before the end of class. Okay? Yeah. I think this one is just like P2600. Try that. What's the password for 2600? Yeah, when in doubt, break into a computer. Okay. So the reason that we have this is going to be primary method for you to give feedback on your progress in the class. And we can discuss issues, questions, etc. You can use this to take notes, but I'm going to suggest something slightly different in the next one. Excuse me. All right. Have you ever used shared lecture notes? Raise your hand if you ever. Okay. So what you do with the shared lecture note is one person is the scribe for that day. You all have the computers open. We all have computers that can be open. You're welcome to keep notes in your own stuff as well. But one person will be keeping notes. And they just type down important things. Of course, you get my slides anyway. That's totally fine. You can keep your notes however you want to. But the nice thing about it, a shared document, is that multiple people can write stuff in it. You can comment in it. You can answer people's comments. Right? So this could be a discussion board. One person should only do it per class and then it should switch. But if you elect not to do this, this is not a requirement. This is what we call a suggestion. Okay. You can insert drawings. If you don't know how to do that, you're missing out. It's really fun. Okay. And you can choose to share this document with me, but also not a requirement. You'll notice there's not a lot of requirements. So there will be 8 homeworks. There will be no exams. I might move this number depending on how mean I feel. It might go up. And the reason for it to go up is that each one is smaller and more approachable. There are competing theories about how material should be presented to students and whether everything being due at the very end creates a mental logjam. And then everything's due at the end and they only do it at the end. That sounds all right? Okay. So for some people that might be the case, and then maybe that's not the best way to do it. But instead of exams, we're going to do check-ins. So for these check-ins, you will have to reserve 5 to 10 minutes and using your progress report and anything else you want to support your argument with, you're going to tell me how you're doing. If you don't make these, you don't pass. Okay. Questions about this? Okay. What is Chat GPT? Yeah. Good. Is it your friend?
No.
Not if you're trying to see how long it takes to get from him. You open up Google Maps and you open up this and you're meant to open up Google Maps. Yeah, that won't help you. So this is not connected to the internet. Even though it looks like it's internet facing. What is the issue with ChatGPT? What does it do? What's that? No. Predictive text. It's predictive. Hold on. It's predictive text. It's artificial intelligence that uses text to look like language. Does it understand what it's saying?
No.
No. Is it very good at bullshitting?
Yeah.
Yes. So what's wrong with this question? Yeah. Nope.
It is just a unit of the wingspan.
Nope.
Oh, it's literally just like the exact same format copy and pasted.
What?
Because like first in Saturn is the least dense gas giants with that, and then like the last sentences are basically the same. Like,
Sure, the last sentences can be the same. In fact, this is true and this is true.
oh, but I was gonna say like same format. Because you can usually tell that this like blank is more dense than this than blank, and like blank is less dense than blank.
Are you asking the top thing what's wrong with that or the green part?
This is the answer.
Oh.
This is the question.
You're asking what's wrong with the question.
No, I'm asking what's wrong with the answer.
Oh,
So even though this is predictive text and people are saying, oh, it's going to revolutionize the world, what's wrong with it? It's very obvious when you see it.
the density's out of order.
The densities are out of order. I asked it to rank the densities. It has the densities and it has not ranked them properly. Okay, this is incredibly obvious to me. If you're trying to understand what the fuck it's saying while also trying to interpret if it's correct, you will be confused. No? Good demonstration or bad? Okay, use this though. Why would I still recommend that you use this? No. We don't care about OpenAI. That's not the point of this class. This class is an educational experience. Yeah.
It's pretty resourceful here. Troubleshooting something.
Sure, yeah. This is like having a friend. And it's like having a really, really smart friend who's sometimes wrong. So you have a question, you don't understand something? See if ChatGPT can explain it better. Right? When I said communication, I mean with everyone. So this is a little bit of a robot, that's okay. Don't get emotional feelings with it, but still use it as a tool. But recognize that it may very well be wrong. Okay? One of your greatest skills as a scientist is determining what is wrong and what is right. Right? What sources are accurate, what sources are inaccurate. You start off in your modern life figuring out things like, oh, the world revolves around the sun and not the other way around. That's like a fundamental truth. Wow, cool. And as you go on, you find out, oh, okay, people who are afraid of like toothpaste, they're probably, all right, people who are afraid that like chemtrails, okay. So you figure that out. That becomes pretty obvious. And then you figure out as you become an advanced scientist, you say, actually, that paper from a very renowned scientist, that's wrong too. Right? That is the process of doing science. And by figuring out what's wrong, you improve science. So you're going to participate with this. Okay. However, we're not a copy paste class. Right? Why are we not a copy paste class? Good. And are there grades in this class?
No.
No. So what's the point of copying and pasting? Who do you have to prove it to? If you don't understand it, you will not understand it during our discussions. You will not understand it throughout the week. You will not understand it when I call on you. You just sit there like, right? Okay. Anyone need coffee? I don't have it. Okay. All right. Questions?
How do you use it?
How do you use it? It's right here. Okay. You're going to type in https chat.openai.com. You're going to make an account. Preferably use your EDU account. It'll give you better permissions. We'll like you more. Say that you're using it for, I think it has like some choices. Don't say you're just using it for fun. They won't prioritize your work.
Sounds really counterintuitive to use your schooling now. It's like, so all the stories like that, we like being used on and stuff.
Yeah.
I think like the very last thing I wanted to do was to say you was schooling more, but that's interesting to know.
So different professors are going to approach this differently. You will certainly find professors, much like when a calculator was first invented, who feel like, well, you really got to learn how to use a slide rule. Just like when a slide rule was invented, there was professors who were like, you really got to know how to use an abacus to count. Now, every time we take a step forward with a tool, there are people who fundamentally disagree with its use, including the chalkboard. People are like, no, you should have to make your own notes. Don't explain things. They have to understand it when you talk. And this is an ancient discourse in pedagogy. These are tools. You will use them. The point of education is to learn. The point of education is not to be graded. When high school, the only thing you had to do is pass the class, get the A, get the number, okay? You didn't necessarily learn in every class. You will be expected to learn in this class. The reason that we have grades is so that I can assess you. But if assessment becomes the only goal, what's the fucking point? Right? Questions? Yeah.
I can agree, but if there's no grades, is it gonna be like put it open or you just gonna
What's gonna happen, folks? Yeah. Yeah. So you're gonna start with this. You're gonna start with this. What is this, everyone? What do you do? Share with me? What do you type here?
Your actual name.
What is that?
Orlando.
No.
Jonathan.
Jonathan and? Okay, good. All right, so you put your name here, and this is the most important part. I need to see it today. Doesn't have to have anything in it, just has to be made. Okay, this will be the way that we communicate back and forth about your progress in the class. You'll type in, this class really sucked. I didn't fucking understand anything you said today, right? That's totally okay. It's a feedback, right? It's the only way that I'm gonna get feedback, and I want it consistently. Now, you don't have to do it every class, but if you do it every class, even just a sentence, like, oh, best part of today was when you were quiet. Great. That makes sense? You get it? Okay. And then, we talked about this part. So for folks who didn't see, we're not gonna have grading on any of the work. What that means though, is it doesn't mean you're not gonna get feedback. So you're gonna do homework, the homework's gonna get marked up, but you won't receive a grade. That make sense? But still do it. What a concept. Where's my sticker? Now I bought I brought a bunch of stickers in from home. So I have a drawer full of stickers. So if you need a reward at the end of your homework, you come in and you can look through my drawer of stickers and you can put that on there. I also have candy. I'm a pro candy consumer. So if you need bonuses, those are the bonuses that we're going to use. Okay. But you need to be turning homework in when it's due. Speaking of homework, I say 8 here. I'm probably going to renege on that. That number's probably going to head towards 10 or 11. That's sad. Okay. Any other questions? Are you good?
So is there like an exam? Was it just like?
What does that say?
Oh.
Okay, but 3 times in the semester we will meet. 5 to 10 minutes. It's not an oral exam. Okay, it's an argument. Okay, so you'll tell me how you think you're doing in the class. You'll give me a letter, you'll give me an explanation for that, and I'll either tell you I disagree with you or I agree. Okay? We'll do this every 5 weeks. And then if the final one, that'll be your final grade. So you don't actually get to say, hi, I want an A, and you haven't come to class the whole time. I'll say I disagree, and you won't get an A. But you'll make an argument for your grade. Okay? Everyone like this, or does anyone want to be graded? Raise your hand if you want to be graded.
What's wrong with this?
No, raise your hand if you want to be graded. Okay, good. Unanimous consent. Everyone was here. No one's online, right? Okay. Okay.
There is.
Is that you? Okay. Well, how did everyone find the classroom? In the syllabus. Interesting. Okay, let's get to that in a second. So at the very beginning of your book, we have this helpful lexicon. It's got every letter in it. You will use it. I promise you, you will use it. You will not know what the fuck is going on sometimes. This will tell you. Okay? If you don't understand a word, you will not understand the physics. Is this a foreign concept? I don't know if I do this differently than other professors, but I tend to focus a lot on what a word means. Okay? Because that will give you the intuition to understand what the fuck is happening. You have a question? Sorry, I wasn't sure if you were opening your mouth. Okay. So just like learning another language, learning how to use these terms properly will help you feel more confident, especially in this class, where we're going to be using a lot of this, like, there's going to be a lot of new words today. I would expect like 100 new words. And you might see similar symbols and get confused. That's normal. You might see the same symbol, like used multiple ways in different slants and just slightly tilted, and you'll have to ask for clarification, right? Prime example is this and that, which is which? What's this one? V. And this is fucked up V. Okay, that's fine. As long as you know what it is, that's fine. So this is V and this is fucked up V. I typically call that new. But we're gonna go with fucked up V right now. Okay, and then what's this one? See? Yeah, very good. Oh, okay. All right. Now I am not a very good drawist. Okay, a scientist. I cannot draw good. So when my handwriting is bad, you will not blame me. You will ask for clarification. Okay? Okay? Yeah. All right. So do you have a question about the class? Is it in the syllabus? Is it in the online grading policy? If it's not in either of those places, you can email me. Slack me. You can raise your hand at any time. Okay. Who filled out the survey? Okay, so you have a computer open. Please read that email, fill out that survey. I need you to fill out the when to meet so that I can set an office hour so that I can make myself available to you to help. I've had office hours in person for a year almost now. And I've had like 6 different unique people come in. I've had about 70 students. So I want to make sure they're accessible. They'll be in a room similar to this. They won't be in my office, but I will bring the same number of snacks. Okay, maybe. Depends on how lazy I am. Okay. Is there such a thing as a stupid question? What do you say? No. There's no such thing as a stupid question. What happens to the information if you don't understand it and you don't ask the question? You understand it afterwards? No, you still don't understand it. And now you have to wait because you don't get it, and I'm just still talking. Okay. All right, who's excited? Yeah. Question? Oh no. I just made you raise your hand. Okay. So we're gonna talk about the content. So oh, I should have said one more thing. There is a class schedule. How many people have the book already? How many people have opened the book already? Okay, how many people have read the book already? Okay, that's honest. Good. Okay. So a lot of this stuff that you're about to see is going to feel like it's hitting you like a freight truck. I will try and go through it sort of slowly. It will help for you to have seen the material before, because then you'll come into class, be like, wow, I tried to read that section. I don't know what the fuck you're saying. Oh, I still don't get it, but I know what to ask later. Right? Because sometimes it'll just be words. You're like, what is that word? What the hell? Right? And then you're like, either ask me in the progress report, you send me a message, then you get that word. You're like, oh, I get it. And now I understand this whole section. Right? Okay, so I'm going to show you really quickly how to find. Where is it? Okay. Oh my God. Oh my God. Okay, so here's the syllabus. There's the when to meet. There's the classroom. Right there. That's where you currently are. Oh, good. Everyone's this is what we're supposed to do. And of course, I should delete this because we're actually not going to do that. And I'll talk about why in a few seconds. We're going to get all the way down to like sonic flow. I think I said all of this here. Oh, I'm going to get rid of lecture tutorials. They won't exist anymore. If you need them, we can put them back in. My idea essentially was that these would be like questions to like check your progress as you go. But I hope that if you're coming to lecture regularly, I've sort of built in enough questions into the lecture that if you're failing to understand those, you can let me know. We can either slow up or speed down as appropriate. Is that okay? So I'll ask for your feedback on lecture tutorials in like 2 weeks, and we'll see how it's going. Okay. Let's go to the schedule. Schedule is boring, but this is it. Okay. How many people have taken vector calc? Everyone, I hope. How many people have taken computational? Okay, so just not you. Okay. That will not only be important like these 3 classes and then onwards, but do you like Python? Okay, so you'll be fine. The math will look very similar to stuff that you've seen before, I hope. And the places where it's not, I will discuss the differences. We will try to do a lot less derivation. I'm just going to show you. And then in the homework, you can really play with the math, try to understand it more intuitively. And because the sheer magnitude of the material is so broad, we're going to try and develop what we call an intuitive sense for physics. So here's a question. Mathematics discovered or created? Created? Anyone disagree?
I think it's
You think it's discovered? Raise your hand if you think it's discovered. Okay, raise your hand if you think it's created. Raise your hand if you've never considered it. Okay, all right, this is a philosophical debate. Neither of you are right, neither of you are wrong. This is called a debate. But essentially, one thing that we want to distinguish, for example, between the ideas of mathematics and physics is that mathematics has solutions. Mathematics is finite, right? And sometimes it represents nature. And physics, by definition, is supposed to represent nature, and it uses mathematics as the language to do so. Is it always successful? No. Fluids, you will see, are very temperamental. They're very annoying. They're nonlinear. We'll talk about that later. Okay. Only in your best examples will fluids be nice. So most of the integrals, most of the mathematics is awful. That's why we have computers. Okay. All right. Questions, comments, concerns before we get into the material? So you have an intuitive feel for fluids, and we're going to tap into a lot of that. It's going to require some of your knowledge from other classes. And if you feel really out of place or you didn't do well in that particular class, that's okay. That's what the progress report is for. I can show you where to look and show you what things to pay attention to. Okay, what's this? Not the words introduction of the words. Bunch of water droplets, correct.
It's a DNA.
Kind of looks like DNA, yep. Is it the right scale for DNA? What? You don't know what scale it is? Why do you think it's big? You can see it with your eyes.
Digital photo.
What?
It's a digital photo.
It's a digital photo, okay. But no one's ever seen like a digital photo of an electron scanning microscope, right?
Because we know water at that scale acts different than bigger, smaller amounts.
Interesting. The scale discussion here. What's unique about this photo? Someone already said what was in it. Yeah, there's surface tension, right? Holding these drops together. And so we already have a sense of the scale because we know how water behaves. Yeah.
It's close to symmetrical.
Okay, it's pretty close to symmetrical. Anything wrong with this picture? It's upside down. How do you know that?
You just feel it.
Why do you just feel it?
The drops are spreading out from each other upwards.
The drops are spreading out. Oh, interesting. In fact, it is upside down. Oh, shit, I have to think of this last. Okay, so the water is coming out of here. In fact, if you look very closely, these are two little knob things, and the water comes out and it forms a flat plane. All right, folks, you can see it here. Or you can walk in, or you can sit closer. Now on, all the text is going to go right here. Okay, so you can see these droplets come off, and you're absolutely correct. So as they move apart from one another, it shows you the direction. Okay. How many phases of matter are there?
But it's like an entire brain thing.
Okay.
Like you've got the main four and then you've got like all this weird shit.
Okay. Okay. So that's the problem with Wikipedia. Yep. So Wikipedia. Okay. So what you said the main four? What does that mean?
All of it.
Solid, liquid, gas. Plasma. Do you believe him? You believe him? Raise your hand if you think there's 4 phases of matter.
Yeah.
Okay, you're in the wrong class. It's fluid dynamics. There are 2 phases of matter. What are they? Solid and fluid. Okay. Everything is a fluid if it's not a solid. So what's a rock? Yes, no, I know. Very good. What's a rock though? How do you define a rock? Hard. Good. Correct. That's the acceptable answer. Anything you can stand on is a rock. Okay,
Okay.
make sense? So she's on a rock, and that's all fluid. There's two types of fluid there. Right? There's liquid and gaseous. Okay. Fluids deform continuously under shear stress. Solids don't. So for example, I would consider this a solid. Would you consider solid? Okay. So I can do that. What happened after I let go? Ooh, magic. Right? Now, you can't see this good, but there is liquid in here. Wow, it moved. Okay, right? So fluids don't behave like solids. That's the first thing that we want to keep in mind. Okay. We're going to talk about shear in a lot more detail later. This one, which one of these two is the solid? Which one of them is this the fluid? Why is A the solid? Right. Yeah, so there's a little bit of force applied here. And the whole thing maintains a shape when external forces are removed, and it does not continuously deform. Okay? When I say continuously deform, I mean these full pieces slide to the right. In fact, this is how we get a lot of fluids to move. For example, if we imagine that this is the seafloor, and this is what we call ocean, and at the top here you have the top of the ocean, wind will pull top of the ocean, air, and move that. Okay. What are those called? Okay. All right. Fluids fall under subcategories. Gases and liquids. Already said that. What's this one on the left?
Yeah.
Gas? What kind of gas? What? What kind of gas is in here? Hot air. Does that say? Hot air balloon. Very good. Okay. And what's this stuff? Water. Water. Yucky, right? Ugh. Who wants water when I could have soda? No. We're a water family, right? Everyone likes water. Okay. Hydrated as fuck. So notice something that happens differently. Right? This is the primary difference between gases and liquids. Here, if I have a hot gas, I need to hold it in. Right? Whereas my cup doesn't need to have a top. Is that true in space? No, you need to have something to hold in the liquid in space too. So this is definitely the fact that gravity is telling you which direction this cup is oriented. If I showed you this picture 180 degrees, you would immediately know which orientation it was, even though you can't quite for that more abstractly. Because you have a very intuitive sense for fluids, you just don't know that you do. I'm trying cracking that right. Okay. Like an oyster. So one thing that we have to talk about here is what's forming at the interface here. What's going on as I fill up that water? Cup goes up. Why is there like why did I include this picture? What is it a picture of?
Surface of the water.
The surface of the water. And I'm specifically talking about something called a free surface. This forms at the boundary of two immiscible objects. What does immiscible mean? Yeah, it cannot be mixed. So even though we have trapped air in here, and for example, this is how fish breathe, this fluid is distinct from this fluid. And for our purposes, we'll consider them immiscible. So these little bubbles will float up and, right? And then it'll have no more bubbles. And there'll be a flat surface, the free surface, that separates liquids from gases. Okay. Questions? Okay. Please write down. You have notes, right? 5 fluids that sometimes behave like solids, or solids that sometimes behave like fluids. Not yet. Don't talk to each other yet. First, write them down for yourself, and then we'll talk. Oh, you have your notes to you. Okay, fine. That's acceptable. Since I specifically requested it. Are you done? Yeah. If you've only come up with 2 or something, maybe check your nearby friend. Ask them what their list is so far. See if you can get up to 5. Come on. I'm gonna break up you guys.
Oh, yeah. Even as a book.
Right. Yeah, it was supposed to be.
Just wanna be friends.
Yeah, I said.
Nice.
Here. No, pitch is like a black, it's like not really hard, but it's like really hard, but if you let it sit, it does flow.
Yeah.
Shout out the answers in the back.
These
ones. Oh my gosh. All right, hold on a second. Yeah, hold on a second. Who's got an example of a fluid that behaves like a solid or a solid that behaves like a fluid? Yeah. Okay, you heard that from them or you heard it yourself? What is it? Well, what is it?
Cornstarch and water.
Cornstarch and water. Very good. Okay, next. Okay.
The mantle here.
The mantle of the earth is what?
Solid.
It's a solid. Yeah, looks like a liquid because it's also under tremendous heat, right? So solid can sometimes just behave like not solid, right? Yeah.
Put gallium to like metal, we can assume like it goes to your hand.
Why is that though? Yeah, what's the temperature? Right, but what is causing gallium to become liquid there?
Our body.
Your body temperature, right? So if you were wearing a glove that was insulated, that wouldn't happen.
That's true.
So that's still solid. Yeah. He already got that. No copies.
Oh.
Anything else?
Don't silly fungi and mantle have like the same properties?
Very similar types of properties, yeah. Now, one of them is slightly different temperature.
Why?
Yeah.
Pitch.
Pitch. What's pitch?
It's not like this, right?
What?
It's like the tar you put on your roof, like seal it, I think.
It's similar, but what are you talking about when you say pitch there?
It's like it's a thick tar-like liquid that slowly flows over many, many years.
Slowly flowing. Okay. Anything else? I'll make an argument. You used one of these in the last week. Okay. Is ice one? No, you can stand on it. Over time, what? Antarctica is big.
Under pressure in a
Yeah, I mean, everything moves under pressure, right? Dun, 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 okay, rocks move under pressure. Talking about a fluid that behaves like a solid or a solid that behaves like a fluid, yeah. Ooh, interesting, interesting. Yeah, so maybe like polymerized materials. Oh, okay, so a lot of people, I think we're grabbing onto things that are continuously deforming. Or that have like small particle sizes, like sand. That way you could think of them like liquids. But here we have an example of something with long polymerization that might have different chemical properties due to the fact that its composition is different. What would be another example of that?
What is it you said?
He said rubber.
Plastic.
Plastics. What are plastics like? Are they like liquids? Are they solids? What is plastic? This shit's ubiquitous everywhere, right? Okay. So in fact, the material properties matter. There's pitch. That's correct. What's this? What's that mean? Whipped cream.
Oh, you put air in.
Okay, but it is cream, is it not?
Yes.
And I poured cream into the bowl.
Oh, you missed it.
You keep saying I mixed air into it. Well, you both have said you mixed air into it as though that suddenly makes it a solid. I just breathed air in. Did I become a solid? No, I'm mostly liquid.
Air in. Liquid?
It's
But it's overall liquid, right? Overall liquid.
Okay, what is this thing here?
Yum.
You say yummy ketchup? Get it.
Oh, come on.
Okay. What's wrong with ketchup?
It's delicious.
It's a lot of sugar. It's all sugar. It's a very American, like, okay, let's just find a way to drink sugar, put on our potatoes. So what is this? Is this a solid or a liquid?
Liquefied solid.
That's not fair. That's not fair. Ketchup is a liquid?
Yeah. What? I can't, yeah, you can't stand my ketchup.
You could not stand like that. Ketchup is standing on its own right there.
No, but they
How big, how much ketchup do I have to stand on for it to be standable?
so much.
Wait,
Okay.
no, if I have like a bucket.
So my point here is that the distinction between liquids and solids is not so clear. Okay? And in particular, when we talked about polymerization, okay, properties like egg whites, they can make your idea of the molecular structure very weird. So in fact, the viscosity of ketchup changes when you apply a force to it. What? So you hit the back of a ketchup bottle. Why does the ketchup come out? Hey, you hit it and there's inertia, good. But also, there is this weird property of ketchup that its viscosity becomes reduced under force. Yeah, it's kind of weird, right? What's the opposite of that? Oobleck. So I heard that word. What is that? You said cornstarch and water. What does it do? Why is it cool? Why does everyone have 100 videos of it?
Hit with a hammer, it shatters.
Yes. You hit it with a hammer and it shatters. What the fuck?
And then you just lay the sand hammer on the hoop.
Right. So how would you describe that with what we call physics?
Non-Newtonian.
Okay, that's the answer. But what's happened? Yes, that's right. But what's happened?
Well, the forces are, it's like the same like forces, but just a different amount of time. So like you apply a lot of, I guess it's just like pressure, or it's like. Is it pressure?
I don't know if it's a time thing.
But you're asking us why that happened?
Yeah. Like, how would you describe like in physics, like when you hit food like with a hammer, it shatters, and then you just like place something on it, that seems to be the
Why? Surface tension doesn't really care about time. So forces, pressures, this is all getting to these idea of stresses and strains, right? So as I begin to hit the oobleck, what happens to the viscosity? What happens to the internal stresses? What's that?
Increases.
It increases. Viscosities jump up in the presence of forces. So as a piece of oobleck tries to move out of the way of your hammer, it suddenly is running against other pieces of oobleck, which then increase their viscosity. So the quicker you do that, shock wave basically hardens the entire material. Is this what happens to water? No. Water just gets out of the way. With the propagation speed that we'll talk about probably tomorrow. Okay. Now, everyone loves videos of oobleck, and this class would not be appropriate if we did not have one. So let's shoot some shit with oobleck. Come on now. You better play.
Hey guys, Backyard Scientist here, and I'm Mark Rober. Today we're going to be doing a bunch of oobleck experiments, and that's just
Okay. So let's shoot some stuff with oobleck. And here we're gonna take a chainsaw, and they have a water balloon and an oobleck balloon. And this will be the oobleck balloon. And I want you to watch the chainsaw spinning like this. Over. Watch what happens when he touches the bottom, and think about before he does it, which direction will the oobleck go, down or out? Whoops. God damn it.
Oh.
Who taught this class? Down or out?
Down.
Well, which one? Okay. I'm gonna, so thankfully it's paused here so that we can make these science experiments in real time. I hate this. They clearly have never figured out that scientists use this for their presentations. Okay. Chainsaw blade goes this way. It's got little razors on it. Balloon, oobleck. Does the oobleck go down, out, up, to the side? What's the oobleck doing?
Out.
Out towards the tree? Raise your hand for out towards the tree. Okay, who's got down? Down? Who's got somewhere in between? Okay, who doesn't want to answer? Okay. That's fine. That's, we can be honest about it. All right, so he's that's good side effects, right? Okay, what happened? Okay. Let's watch it slowly because that's the whole point of slow-mo, guys. Oh, interesting. Which direction is it going? Look at that. Look at that shape. The whole thing still looks like a water balloon, but now it's moving off to the right. Would you expect water to act like that?
No, it would just.
Water would go which direction? Just down. Would it stay the shape of water?
No, yeah, for a little bit.
Okay. All right. All right. We need to have intuition here. So let's see. Yes, fluids are really cool. Okay, here's the water. And it will go straight down. Not even a lick up to the right. Okay. He's going to shoot it with a BB gun. That's not a rifle. So here, let's see if we can make some predictions. So what are you going to see there? You just shot it. BB gun, very small. Yeah. You think it's going to get stuck? Okay. So a small object, it'll get stuck. It won't pass through, right? Okay. That was water, by the way. So here's your oobleck. Huh? Oh, I'm just freaked out. Why would this thing respond to my just normal clicks? Yeah. Okay. Is that what you expected oobleck to look like? Still kind of look liquidy, right? You can still kind of see the hole, but it's not very impressive. Okay. I think they do it with a larger caliber. In fact, it does pass all the way through. That's the water, by the way. It behaves almost exactly like water, right? So the difference there was another way to say that. This is more water. You said the scale. Another way to say that is. Let's use some physics words here. Okay, there's a little bit of mass there. Mass is doing what? Nope. It's decelerating. And it's imparting forces, momentum, right? Energy exchange. Okay. There's a pressure, right? That pressure is a small area and a small force. Okay, so that pressure is small. So this fluid under a little bit of pressure, very small deformation. Okay. All right. So what is he gonna do? When is he gonna use the big one? Oh yeah, there we go. So now what happens when we shoot it with a golf ball? Okay, so now you expect it to.
Go with the same.
Okay, why? Okay. Anyone disagree?
Projectile bounces off of it, if that is solid.
Wow, you want it to bounce off. Okay. All right, that's bold. Bold. Anything else? I might be right. I mean, that would be very weird for a solid, right? Or for a liquid. Right? That's kind of like a YouTube video. This is the point of predictions. It's definitely not going to do what the water did, right? Water's just going to pop. So something's going to happen. So you have to make a prediction. Is that it? Anything else? Yeah.
I agree with Ryan. I think, gold in this new day, I think is about-
Okay. Okay. Bigger forces, something weird. Okay. Let's find out. Okay. What's the problem with YouTube? I'm gonna kill this computer. Yeah. Now you see that was the golf ball in the beginning. All right, so let's watch the slow video. There's your golf ball. And it almost stopped it. It almost stopped it. But look what happens to it. And of course, all of those pieces that come off of it, they behave like solid. They're totally shocked. Right? And then the rest of it starts to just drip down normally because it's back to its liquid form. So in fact, the material itself matters, right? That's cool. Can't deny that. Fluid's good. Okay, so what makes a fluid? Yeah, why fluid? Why not solid? Good. Why? What was that? Okay, viscosity I don't tend to use for things like solids. What about the solid lets me stand on it? What?
It's permanently deformed.
Uh-huh. Is that a solid or a liquid? This was just fun. Sorry, just exploding stuff in the background. No one can pay attention to me because shit's exploding. Okay, let's talk about the continuum hypothesis. I'm sorry, you can watch that video on your own. Okay. So what is the continuum hypothesis? It says, pretty simply, that at a microscopic scale, all of these little molecules, almost slightly bigger than others, but they're little, they collide with each other and they form a statistical ensemble. You heard this word before? Ensemble?
Yeah.
Who's taking that next? Oh, okay. You're in for a treat. Okay. Oh, this is gonna make this couple lectures smart. All right. So microscopic quantities that you can measure for the molecules are their mass and their velocity. Maybe their charge, but we're not gonna get into that. Anything else we can measure for a molecule? That we care about? Not really. Everything else is kind of secondary to that. Spin, rotation, vibrational energy, those are all things we can deal with later. Okay. Mostly it's just mass and velocity. There's a lot of velocity, we call that. What? Fast, good, that's fine. Let's work, oh, another word past that. Molecule fast. Hot, good. What is hot? Lots of, okay, you just now said energy. So how did you get from energy from that? Oh, kinetic energy of the molecule. Okay, okay, I see it. Good. So in fact, we want to examine this average behavior. So we are going to talk about macroscopic quantities. We talked about one of them already, which is temperature. Another one of them we've already been using quite often is pressure. Things like the density, or as we see in fluid, bulk flow. Bulk flow. What does bulk mean? It means as a whole, and then flow. So we're going to talk about fluid particles in a little while. And instead of thinking of looking at one tiny drop, we're going to follow like a box. So pick an Amazon-sized box, and then move it through the fluid. Bulk flow. Okay? And this is very distinct from the life of the individual molecule. Everyone in the molecule running around that race, and then the whole place is fixed. So when is this approximation valid? Very good. What a good reader. What did you say? Did you understand what you said? Okay. What's unity? Okay. Okay. Unity is a special math word that is just because they didn't have enough cool words because they suck. It's just one. No respect for mathematicians in this room. Don't tell my mathematician friends. So this is a way of talking about, and we'll do this a lot. Knudsen is a name, and it's a person who did something good and gets a number named after them. This is cool, right? Asteroids, okay, you can have anyone can name an asteroid. Not you, but people who work. But like when you work in the field for a long time, you get an asteroid named after you. If you did like a really good job, you get a number named after you. If you found out something really cool, you get an equation named after you. Right? That's like the. Now, if you're Bernoulli, there's already 4 Bernoullis, you're fucked. Now no one knows which Bernoulli did the thing. Right? Okay. So Knudsen is it's a dimensionless parameter. And we're going to talk about these types of dimensionless parameters. And we're going to talk about them with respect to unity. So we're going to talk about them being really large or really small. And that'll tell us something different about the physical system. Okay. So we say that when the Knudsen number is less than unity, we will call it a fluid. Okay? What is it? Oh, none of you did read it. Okay.
You said you have to do a mean free path or something like that.
Yeah, it does have to do with the mean free path. Good. So it's L over L. Okay. Recall that if you simply write down the letters exactly as they are, you will be confused. You want to understand what it means. L here is the mean free path. This L is the length scale of interest. And we want this quantity to be less than unity. What does that mean? And what do all these things mean? What are you most confused about when I just told you? Mean free path. What's the mean free path?
The distance that a molecule travels before it collides with another.
Perfect. So imagine that I'm a molecule and I'm in this room and I don't have a frame. Just like go on. Bang. Okay, and then I bounce off this. Bang. Okay, and then bounce off this. Bang. Right, and then bounce off this. Bang. And so if I measure up all of those distances and how many collisions there were, just divide those two numbers. I got mean free path. Okay. It's like this. Follow a single particle. Boom. Okay. So the number of collisions, right, will be high when the mean free path is small. Here's mean free path. Here's L. What is L? Length scale. What does that mean? Yeah.
The shortest distance from the starting to the end,
Like this way?
like the blue to blue.
Blue to blue. You could, yeah, that could be a length scale. Does this have to be pre-selected, this length scale?
Maybe you can adjust it for this, depending on the situation.
Exactly. So this dimensionless parameter, the Knudsen number, is going to be your tool to decide whether or not this thing that I'm considering is a fluid on these scales. This is a length scale. If I say to myself, okay, well, I want to look at something that's only about 2 angstroms wide. I want to look at a parcel of fluid that's 2 angstroms wide, and the mean free path is a 1/10 of an angstrom. Is that a small number? I don't know. Is the fluid a fluid there? Is the continuum hypothesis valid? I don't know. You could take those numbers, right? You say, how small can I make my fluid before it really stops being fluid? Right? Similarly, what if L is really big? What if the mean free path is really large? That is, I don't have a lot of collisions. Then it's not really fluid. Okay. And we'll talk about the idea of length scale in a lot of detail in this class. Why not working? Okay. So when is the continuum hypothesis invalid? Okay. What happens at the top of the atmosphere?
If it goes off into space,
Mm-hmm.
we're unaffected by Earth's gravitational pull.
Good. What would the length scale be there? What's that?
Like all the way up at the end of our atmosphere.
Yeah. What's an appropriate length scale? Kilometers, sure. I'm trying it right now. Okay. So length scale, I'm going to show you some examples. I'm going to show you that it means what you want it to. In the process of talking about, say, let's say I have an Amazon-sized box. Okay, what is that? Maybe like 3 feet. 2 feet. Now my length scale is 2 feet. Good. What's the mean distance between collisions in that 2 feet? No, you can guess it. We're gonna make educated guesses in the class. What's the size of a molecule? Good. How small? Good. Microscopic, so smaller than. Good.
You want to get to the opposite.
So is it the size of a micron? Somewhere in between a micron and a nanometer. Nanometer is what wavelengths of light are like. Right, 700 nanometers is what the edge of your eye can see. Micro, so microscopic and micro as an adjective don't mean the same thing.
Okay.
So microscopic, for example, when we're talking about the length scales here, they're not very big. Certain molecules are larger. Certain polymer chains are large enough to see. Right? But when we're talking about a fluid, we want to think about what is the distance between. So if you said anything between a micron and a nanometer, that's fine. But depending on your fluid, that number will be different. Depending on the temperature, that number will be different. We'll talk about why in a few seconds. Okay, let's try this length scale question again. At the top of the atmosphere, said kilometers. What's the length scale like at the top of the atmosphere? How's the density at the top of the atmosphere? Small, so not many things to collide with. You're traveling on some like life path, you're not seeing any of your friends, you just go forever, right? Yep. Increases, yeah. So in fact, the mean free path might be really large compared to a kilometer. And then I'd say, well, it's not really a fluid. Okay. What about this second one? What's the supersonic flow? And the bulk flow is very fast. Good. In fact, it's moving faster than sound. Super above sonic sound. So this will be a compressional fluid. It's compressing because it's moving faster than the speed of sound. Yeah. So not only do we make things go that fast, they already do that fast in nature. What's an example of a supersonic flow in nature? What's that? Rain is very, very slow.
Yeah, thank God.
That was such. Its rain was supersonic. You're not wrong in sort of staying on Earth, but you won't find your answers here. Light is not a fluid.
So, so not on Earth.
What? Sure, yeah. Storms on Jupiter could be a perfectly a perfectly acceptable answer, but I'd go with, galactic jets, supernova, the sun, stuff that has, larger sources of energy that can make stuff go fast. So for example, these solar wind events, these ones that like throw off a massive amount of energy, those will become supersonic. Okay, so what happens with supersonic flow? The length scales become really small compared to the mean free path. And it's not really, we can't treat it in the same way. Yeah.
You said we do that? Why would we need to make flow go supersonic?
Well, sometimes you want to go fast. If you want to go fast, you got to make flow go supersonic. Otherwise, you can't go through the flow. Does that make sense? You can make a plane go vroom, right? Do you want to break
through the engine of the plane faster than you're going to the plane?
Exactly. You typically want to stay in front of the engine. So if you go behind the engine, you're dead. And if the engine goes through you, you're double dead. Right? So exactly like what Andrew was saying. So you want it to go fast and you want it to bring you with it. So we will split air at supersonic speeds. And then we'll push through it. Now you forget, for example, you think to yourself, I'm driving in my car and everything's going by me. But really, when you're outside of the car, it looks like you're going by everything else. You'll see the same argument with fluids. So if we move through the fluid this way at supersonic speeds, it also looks like the fluid is moving past you at supersonic speeds. Right? What about flow around a single cell organism?
Well, wouldn't that provide?
Organisms just like being eaten up by molecules.
Yes, but they're also bathed in them and they're like eating them like. I mean, they don't have faces or arms like that, but you know what I mean. So what changes when I talk about flow around a single cell organism? Which of these two is important to consider? The length, right? Because the single cell organism there is the one that I care about. The flow around it is now going to be the length scale of the organism. If that's small, then this thing becomes close to unity, bad approximation. Okay? What happens at the bottom of the ocean at great pressure?
Would that mean more collisions?
At great pressure, good. So you think, okay, maybe the mean free path is shot up or shot down tremendously? What's the length scales here?
Even greater.
Kilometers, yeah. So we're good. We're good. As long as that denominator is huge, we're good. So we have like, yes, maybe this is slightly larger. But under greater pressures, it gets smaller. So we're chilling either way. What about narrow flow paths, like a really thin tube?
Or some people know, need to know.
Mean free path is set by what? I haven't defined it yet. But so far we've talked about mean free path as being set by. Yeah, collisions between nearby particles. So density will matter, temperature will matter, not the region of space that you're looking at. In fact, the word narrow here tells you that your length scale will be small. Okay, so I've run out of time. So this is what class will be like. You need to send me today your document with the progress report. If you don't know my email, come on, guys. No. 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 It's the one that you got an email from. Yeah. Sure, yeah. But you need to share permissions with me anyway, so do that. Do it with either one is fine, I guess. That's the second one. This is one email, and that's the first email. Oh, yeah. You did it. Yeah. These are dots. Sorry, this is supposed to be a J.
Send it to both.
No, either one is fine. Cheese and crackers. Oh, copying and pasting will be such a demand. Oh my gosh. What do you mean?
Like,
Why not? I got 4 names. You gotta use them.
What's the MJ?
MJ, Michael Jordan. No, just kidding.
You're MJ.
It's Mary Jane, actually. Mary Joanne. Any questions? No. Can I keep my secrets? You're all trying to get my secrets.
So why do you forget?
Oh, that's true. That's a good question.
Give us the book. I'll look it over.
We are out of time. Yeah, okay. Just want to make sure. Why does the Zoom say that we still have like 45 more minutes? Screw Zoom. It must have stopped and opened back up. Okay, well, I'll upload those. You probably won't be able to hear half of me because I walk around like an idiot, but maybe I'll get a microphone. If you need a book, come talk to me. Yeah.
Why does this say lab 2200 on Wednesday? Yeah.
Where does it say that?
Cause like it just downloaded my notes saying it was Monday was lab.
I mean, this is when I think it is. So that would be great if it was when I think it is, because I'll be there.
Yeah.
how do you
Or it was, Mike, I really scan. Yeah.
Do you have a conflict, Kobe?
No, I don't conflict.